So these large language models, they're amazing for reasoning, right?
Right.
But they're huge. And getting them to do complex stuff, like chain of thought, means generating loads of tokens. That gets slow, and it costs.
Yeah, that's the bottleneck. And it's
Yeah.
why people are looking at smaller models, SLMs. They're much, much faster.
But there's a catch.
There is. When you distill these SLMs from the bigger ones, their reasoning paths, well, they tend to wander off. They don't quite follow the same logic.
Leading to mistakes.
Right. You lose accuracy. The paper mentions a specific example, actually. An R1-1.5 billion parameter SLM gave different final answers, 45% of the time, compared to the big 32 billion parameter LLM on a math benchmark, AME.
Wow. Nearly half the time it ends up somewhere different. So it's speed versus getting the right answer.
That's the classic trade-off. Which brings us to the paper we're digging into today. It's called R2R, Efficiently Navigating Divergent Reasoning Paths with Small Large Model Token Routing.
R2R. Okay, and they have a specific insight into this problem.
They do. They found something really interesting. The reason SLMs perform worse isn't because they're just generally bad or wrong all the time.
Yeah.
No. It's because their reasoning paths split off, they diverge, because of differences on a really small number of specific tokens.
Just a few key moments throw things off.
Kind of. Most of the tokens an SLM generates are actually identical to what the LLM would have generated. Or, if they are different, the difference is harmless, like, phrasing variations.
Like saying let's instead of let us.
Yeah, that's the example they give. That's a neutral difference. It doesn't change the meaning or the logic.
But some differences do matter.
Right. Those are the divergent tokens, maybe a calculation error or choosing a word that shifts the meaning. Those are the ones that send the reasoning down a completely different path.
And these crucial divergent tokens are rare.
That's the key finding. They looked at 7.6 million tokens. The SLM output was different from the LLM about 11% of the time, but only 4.9% of the total tokens were actually divergent. So less than half of the differences actually caused a problem for the reasoning path.
So most differences are just noise, essentially.
Or harmless variations. The divergence is concentrated.
And the R2R solution, it uses this insight.
It does. The idea is, what if you could use the efficient SLM for most of the work, but then selectively call in the powerful LM just for those few critical path-divergent tokens?
Intervene only when the path is about to really split.
That's the goal. Get the LM's accuracy where it counts, but keep the SLM's speed for the bulk of the generation.
Okay, so our mission for this deep dive is to unpack how R2R pulls this off and what results they got based on this paper.
Oh, sounds good. And just to reiterate the scale of the problem with LLMs, we're talking potentially thousands of tokens for a single complex query. That's a lot of compute.
Right, and distilled SLMs, while faster, suffer that performance drop. You mentioned the R1-1.5B versus the 32B model, a 4.8 times lower accuracy for the small one.
Yes, a huge gap. And again, the paper argues this gap isn't from uniform weakness, but from errors accumulating after these specific divergence points.
The 11% difference versus the 4.9% divergence.
That's the core statistic they build on. Neutral differences are fine. Divergent ones break the reasoning chain.
Okay, I get the problem and the insight. How does R2R actually implement this selective LLM usage? What's the mechanism?
So R2R uses what they call a neural token routing method. It's different from older approaches.
How so?
Well, some previous methods did query-level routing. You'd look at a query and decide upfront, okay, this one's easy, send it to the SLM, or this one looks hard, send it to the LLM.
So one model handles the entire response.
That's right. An all-or-nothing choice per query. Another common technique is speculative decoding.
Ah, yes, where the small model drafts ahead.
Kind of. The SLM generates a draft of several tokens, and then the LLM checks it. If the LLM would have produced the exact same sequence, great, you keep it. Fast.
But if there's any difference,
Yeah.
even a neutral one,
Then the draft is rejected from the point of difference onwards. You have to roll back, use the LLM's token, and start drafting again with the SLM. This checking and potential rollback can limit how much you actually speed things up.
especially if many differences are neutral, like let's versus let us, you'd be rolling back unnecessarily.
That's a potential issue. R2R is different. It routes at the token level, like speculative decoding, but it's specifically trying to identify and correct only the divergent tokens, not just any difference.
So it aims to let the neutral differences pass.
Yes, and when it predicts a token is likely divergent, it calls the LLM immediately for just that one token to correct the path before it goes wrong. No need for periodic verification and rollbacks of whole chunks.
A much more targeted intervention. Okay, how does it know if a token is likely to be divergent, especially during inference when it only has the SLM's output?
That requires training data. They developed an automatic pipeline to label tokens as neutral or divergent.
How did they generate that training data?
It's a neat process. First, get the reference path by having the LLM generate the full response,
A correct answer.
the desired reasoning path, yeah. Then, use the SLM to essentially trace along that path, predicting tokens. For about 90% of tokens, the SLM prediction matches the LLM exactly. Those are easy, they're marked as use SLM and set aside.
So most tokens are straightforward. What about the 10% where the SLM predicts something different?
That's where the interesting part happens. For each of those differing tokens, they generate two continuations using the LLM. One continuation starts from the SLM's different token, and the other starts from the LLM's original token.
Okay, two potential paths forward from that point of difference.
Right. Then they use another powerful LLM. They used Quinn 2.572B as a kind of judge, or verifier.
To compare the two paths.
Yes, using a specific prompt. The verifier looks at the two continuations and decides. Did that initial difference from the SLM lead to a meaningful change in logic or outcome, divergent, or was it just a surface-level variation, neutral?
And that judgment provides the label for the original differing token.
Correct. Use LLM if it was divergent, use SLM if it was neutral. They mention using a sentence-level comparison for practicality in this labeling phase.
That gives them the training data. But at inference time, the router needs to predict divergence before it happens, using only the SLM signals. What signals work?
They found a couple of strong indicators within the SLM's own processing. First, the SLM's output probabilities, the logits.
What about them?
Tokens that turned out to be divergent showed much higher entropy in the SLM's prediction, about 3.8 times higher on average.
Higher entropy means the SLM was more uncertain about its prediction.
Yeah, less confident, more spread out probabilities. That uncertainty correlates with potential divergence, so the router looks at the SLM's top predicted logits.
Interesting. What else?
Token frequency. Tokens that appear less often in the training data were more likely to be divergent.
Maybe the SLM just hasn't learned those rare cases as well.
That seems plausible. So the router also considers the token's embedding, which represents the token itself, to capture this frequency aspect.
So SLM uncertainty plus token rarity. Anything else?
It also takes the SLM's last layer hidden states as input, providing broader context.
And the router model itself, is it big?
No, it's designed to be lightweight, just a 56 million parameter feed-forward network. Takes those inputs, logits, embedding, hidden states, and outputs a probability. How likely is this next token to be divergent?
Okay, and then during actual generation, how does the routing work?
Step by step. At each token position, the SLM generates its potential output and the associated signals. The router takes these signals and calculates the divergence probability.
Then compares it to a threshold.
Right. If the probability is below the threshold, the system just uses the SLM's predicted token, fast and efficient.
And if it's above the threshold,
Then the system pauses the SLM, calls the LLM, and asks it to generate just that single token.
the LLM provides the correction.
Yes.
Yep.
That LLM-generated token is used, and then control goes right back to the SLM for the next token prediction. It steers the generation back on course immediately.
So minimal LLM intervention right at the crucial moments avoids those big rollbacks.
That's the core idea. Minimize LLM use, maximize path quality.
So the crucial question, did it work? What did the results show?
They tested it across some challenging benchmarks. Math reasoning with AME, coding with Live Code Bench, and difficult question answering with GPQA.
And the key trade-off, efficiency versus performance.
That's where it gets interesting. Let's look at the numbers from their tables and figures.
Okay.
R2R, using an SLM and selectively calling the LM, ended up using an average activated parameter size of about 5.6 billion. That's blending the SLM, the router, and the fraction of time the LLM is active.
5.6 billion on average. How did it perform?
It achieved a 46% average accuracy across those benchmarks.
How does that stack up against just using a distilled SLM?
Well, the R1-7B model, which has 7 billion parameters, only got 28% accuracy, and the R1-14B model, double the size at 14 billion parameters, got 43% accuracy.
So R2R, with fewer average parameters than R1-7B, got significantly higher accuracy and even beat the R1-14B model.
Yeah, it delivered about 1.6 times the accuracy of the 7B model and slightly outperformed the 14B model, all while being smaller on average than both.
That does sound like a better efficiency-performance balance. What about compared to the base models?
Compared to the small R1-1.5B SLM, which only scored 10%, R2R was 4.6 times more accurate. And it did this while only needing to call the big R1-32B LLM for about 11% to 15% of the tokens.
And how close did it get to the full LLM's performance?
The R1-32B LLM scored 50% accuracy. R2R, at 46%, retained 92% of that accuracy.
So nearly LLM-level accuracy with way fewer active parameters on average.
That's what they argued. It pushes the Pareto frontier, giving you a better combination of cost and quality than the other methods plotted.
Okay, that's parameter efficiency. What about actual wall clock speed? Did they measure that?
They did. On the A benchmark, running on NVIDIA A800 GPUs,
Yeah.
R2R clocked in at 84.3 tokens per second.
How fast was the big LLM, the R1-32B?
That ran at 30.5 tokens per second, so R2R was about 2.8 times faster.
Nearly triple the speed for comparable accuracy. That's significant.
It is. It was also faster than the distilled models, about 1.6 times faster than the R1-14B model.
Faster than query-level routing, too.
Yes, those methods were around 55, 57 tokens per second in their tests, so R2R was roughly 1.5 times faster than them as well.
And speculative decoding, some of those are pretty optimized.
They compared it to methods like Eagle2 and Haas, which were in the low 70s tokens per second. R2R came out ahead in speed in these evaluations, too.
So faster across the board compared to these alternatives in their tests. Did they do any ablation studies, like removing parts of R2R to see what mattered most?
Yes, a couple of key ones. They tried training the router to correct all differences, not just divergent ones.
Like speculative decoding tries to match exactly.
Sort of. What happened was accuracy actually went down by 1.4 times compared to standard R2R, even though LLM usage was similar.
Really? Why would correcting more differences hurt accuracy?
The paper suggests that forcing the SLM to mimic every little phrasing choice of the LLM might disrupt the SLM's own natural generation flow in ways that are counterproductive. Targeting only the meaningful divergences seems key.
That really reinforces their core idea. What else did ablations show?
They confirmed the importance of the predictive indicators. Removing the SLM logits, or the token embeddings, from the router's input reduced the router's accuracy in predicting divergence.
So those signals, uncertainty and rarity, are genuinely useful. Did they look at when R2R decides to call the LLM during generation? Is there a pattern?
They found it routes to the LLM less often during the final reply part of the output compared to the intermediate thinking steps, like in chain of thought.
More correction needed during the reasoning process itself.
Seems so. And even within the thinking process, it tended to use the LLM more often right at the beginning of a thought segment, maybe to set the direction, and also near the end, perhaps for conclusions or deciding the next step.
That feels intuitive, actually. Setting up and wrapping up steps might be more critical.
And they noted this behavior just emerged from the training. It wasn't explicitly programmed.
Okay, so let's wrap this up. R2R seems like a clever way to get the best of both worlds, harness the reasoning power of LLMs, but with efficiency closer to SLMs.
By being smart about when to use the big model only for those rare, critical moments where the reasoning path is about to diverge significantly.
Avoiding the overhead of constant LLM use or the potential inefficiencies of other methods like simple speculative decoding or query routing, the results suggest it improves that efficiency-performance trade-off.
Based on the benchmarks in the paper, yes. It appears to offer a new point on that curve.
Now, the paper did mention some limitations, right? It's not a perfect solution yet.
True. They pointed out their current approach assumes greedy sampling, basically, always taking the top predicted token. And they also note that fully realizing the theoretical speedups might require more system-level engineering and optimization.
So practical implementation might still have some hurdles.
As is often the case. But the core routing concept seems promising.
It does. And it makes you think. This idea of identifying and correcting tiny yet critical path-altering moments.
Right.
How else could that kind of granular intervention change how we build or use AI, maybe even beyond language?
That's a great question. What other complex processes have these subtle but crucial decision points where a small correction could keep things on a much better track? Finding those divergent tokens in other domains, that could be really powerful.